Hello everyone, I am SMitra from the Department of Earth Sciences, IISER, Kolkata. Today I am going to present to you our research on the seismotectonics of the Eastern Himalayan and Indo-Burman plate boundary system. Before I present to you this research, I would strongly recommend that you go through my YouTube video on the crustal structure and evolution of the Eastern Himalayan plate boundary system in Northeast India. This will introduce you to the structure of this region and will help you understand the earthquake seismotectonics. Let me quickly introduce you to this region that we'll be talking about. This is a map of the earthquakes across the Himalayas and India over the last 50 years, which are of magnitude greater than 5. These are plotted by color coding them as white for shallow ones, yellow for intermediate depth, and the orange ones are the deep focus earthquakes. What I show on this map is the Eastern Himalayan plate boundary system, which is almost a third of the entire Himalayan arc, and this is the region where you have earthquakes not only at the plate boundary but also away from the plate boundary. Next, what I'll do is I'll zoom into this region and I'll talk about the major tectonic units. This is the region which I refer to as the Eastern Himalayan plate boundary system. To the north you have the Eastern and the Sikkim Himalayas. This is followed by the Brahmaputra Valley, which is the foreland basin south of the Eastern Himalayas. To the south of the Brahmaputra Valley you have these elevated spurs of rocks in the Shillong Plateau and the Mikir Hills. And south of the Shillong Plateau is the Bengal Basin sediments, and to the east of it is the Indo-Burman plate boundary convergence zone. The most important faults in this region, which I'll be referring to throughout my presentation, are the Dauki fault, which bounds the Shillong Plateau to the south, the Oldham fault, which is a hidden fault somewhere in the north of the Shillong Plateau, between the Shillong Plateau and the Brahmaputra Valley, and the Kopili fault zone, which lies between the Shillong Plateau and the Mikir Hills. To the south of this, hidden underneath the sediments of the Bengal Basin, is the Eocene hinge zone, which is a gravity high, which most probably marks the paleo-continent ocean boundary between India and the Bengal Basin. From previous studies of the structure across the Shillong Plateau, the Brahmaputra Valley and the Eastern Himalayas, which is plotted onto your left, and from earthquake depth distribution across the Indo-Burman convergence zone, we now understand that this zone of the Eastern Himalayan plate boundary system is a zone of interaction between the under-thrusting Indian plate beneath the Himalayas and also of the subduction which is between the Indian plate and the Burman microplate. In case you haven't had a chance to listen to the presentation on the velocity structure, I will summarize the main results in this slide. So what we have seen by looking at the joint inverted shear wave velocity structure using receiver function and group velocity dispersion data is that the crust underneath the Shillong Plateau and the Brahmaputra Valley is continental in nature with an average shear wave velocity of 3.5 kilometers per second. The thinnest crust lies underneath the Shillong Plateau, which is about 30 kilometers thick, and there is an offset or a strong flexure towards the north of the Shillong Plateau, which increases the crustal thickness underneath the Brahmaputra Valley by about 9 to 10 kilometers. To the south of the Shillong Plateau, underneath the Bengal Basin, the crustal structure is very different. It's a transitional crust with an average Vs of 4 kilometers per second and an average thickness of 18 to 20 kilometers. This transitional crust is overlain by a thick pile of sediment which is about 18 to 22 kilometers thick with a shear wave velocity of 3 kilometers per second. So the structure across the Dauki fault south of the Shillong Plateau is completely offset by about 12 to 13 kilometers across the fault. In this context, now let me outline the two major outstanding questions that will be addressed through this presentation. The first one is to understand the earthquake source mechanism and its relationship to the structure in this region. And second is to understand the role of the bounding structure like the Oldham Fault, the Dauki Fault, the Kopili Fault Zone or the Eocene Hinge Zone in accommodating the convergence that we see across Northeast India. In order to answer these questions, we will first compute earthquake source mechanisms of earthquakes which happened in this region over the last 30 years, which are plotted as stars on the map on your right. So there are 35 earthquakes above magnitude 5 for which we will be using teleseismic waveform inversion. There are 7 earthquakes which have magnitude between 4 and 5. For these we will be using the local waveform inversion, and then we will incorporate 15 other earthquakes from previous studies. I'll use a couple of slides to briefly tell you about the methodology that we are going to use, which is going to be applied for both the local waveform inversion and the teleseismic waveform inversion. The first step is to relocate these earthquakes using phase travel time data, which has already been done. And then what we do is we use the waveform fitting to get the earthquake mechanism. Imagine that you have an earthquake source which produces a recorded waveform which you see on the right, and this is a convolution of the earthquake source with the earth structure. Now if we actually have a recorded waveform, we can go from the recorded waveform to the earthquake's source by using an inverse technique. This is how the waveform fitting is performed. So we assume a source for the earthquake, convolve it with the earth structure, and then compute a synthetic waveform, and then compare it with the recorded waveform that we have. And if it's not going to fit the recorded waveform, then we keep on iteratively updating the earthquake source till the point the recorded waveform and the computed waveform actually match each other. So once we have a minimum misfit solution, that becomes the earthquake source mechanism for the given earthquake. So we use this method to actually calculate the source mechanisms of earthquakes across this Eastern Himalayan and Indo-Burman plate boundary system. So I'm now going to present to you the results of the analysis. So I'll start with the earthquakes in the Eastern Himalayas, which is to the north, and then progressively go towards the south. I have plotted two maps here. The one on the left actually shows you the focal mechanisms, which are plotted as these beach balls, and on the right are the slip vectors, which have been plotted by using the most probable fault plane and then looking at the relative motion of one block with respect to the other. In the plot to the right, what we do is we plot it in an India fixed frame. So we hold down India and we see how the Himalayas are moving towards or away from India. So from the focal mechanisms, we can see that all the shallow earthquakes which are within 20 kilometers depth, which happen within the Himalayan wedge, are low angle thrust fault earthquakes. And from the slip vectors, we can clearly see that there is convergence between India and the Himalayas. Or in other words, if you have an India fixed frame, the Himalayas are actually overriding the Indian plate. Next, we move on to looking at earthquakes in the region of the Brahmaputra Valley, the Shillong Plateau and the Mikir Hills. So here I will first focus on these earthquakes which are marked by the box, the red box on your left map. So these are earthquakes which are in the mid to lower crust, which is very important to note. And these are also thrust earthquakes along the northern edge of the Shillong Plateau. So these plains are basically south dipping plains which have reverse fault motion. So if you look at the slip vectors on the right, you can see that obviously these show you thrust faulting on faults which are dipping towards the south. Next, we look at the earthquakes in the Kopili fault zone, which is marked by the red box. So what you can clearly see again are that these earthquakes are in the mid to lower crust, and the sense of motion, if you consider the northwest southeast oriented plains as your fault plains, then these are dextral strike slip earthquakes which happen in the Kopili fault zone. It's not only limited to the Kopili fault zone, it also extends further towards the northwest underneath the Himalayas, happening within the Indian plate, and also further southeast underneath the Indo-Burman convergence zone, where you can see these strike slip earthquakes. So obviously the Kopili fault zone has these dextral strike slip earthquakes extending beyond the region between the Himalayas and the Indo-Burman convergence zone. So what you can see from the slip vectors on the right is that these earthquakes form a bookshelf of dextral strike slip motion, and then you have this motion which extends beyond the region between the Shillong Plateau and the Mikir Hills. Now let us look at the region south of the Shillong Plateau, which is within the Bengal Basin. Remember that this is the region which has the most interesting crustal structure. So it's a transitional crust which is about 18 to 20 kilometers thick and is overlain by sediments and sedimentary rocks which are about 18 to 22 kilometers thick. So you have a crust which is about 40 kilometers thick, with half of it being the transitional crust and the other half on top being sediments and sedimentary rocks. What we see from the earthquakes in this region are that they are all deeper than 20 kilometers and shallower than 40 kilometers, which means that all these earthquakes are in the transitional crust in the Bengal Basin. The other thing that we need to note on the map on our right is that the paleo-passive continental margin between India, the continental crust of India and the oceanic crust to the south of it lies along that Eocene hinge zone. Obviously, with the rise of the Himalayas, you have all these sediments which have been derived out of the Himalayas and deposited through the Ganges and the Brahmaputra rivers into the Bengal Basin, which fills up this basin and forms this thick pile of sediments. But underneath it, you still have the paleo-passive continental margin. What we think is happening in terms of the earthquakes are that these are all sinistral strike slip earthquakes which are in the Bengal Basin in reactivated paleo-rift structures. I'll explain this a bit better by using schematics in the next slide. So here, if you take a cross section across this region of the Eocene hinge zone and into the Bengal Basin, imagine a situation where the Indian plate had not collided with the Tibetan plate and this was a passive margin boundary. The schematic that you see on top actually shows what the structure across this passive margin would look like. So you'll have these rift faults which would be at the edge of the continental crust and then would thin out and transit into the oceanic crust. So what we see underneath the Bengal Basin is this transitional crust with all these paleo rift faults hidden within them. And overlain on top of it are the sediments which have been derived out of the Himalayas after the collision of India with Eurasia. So now, obviously, if you have compression in the north-south direction, there is always a chance that these paleo rift faults will be reactivated in this region. Let me use another schematic on the next slide to explain how we think these faults have been reactivated. Now, because of the convergence between India and Eurasia, which happens at a direction of north 20 east, which is marked by the red arrow on the right hand plot, you would see that these faults which are within the transitional crust would actually get reactivated under compression. But how would they be reactivated? These faults are oriented at a oblique angle to the direction of the north 20 east convergence, and therefore they would get reactivated in strike slip motion. So the strike slip motion reactivation of these faults would lead to sinistral strike slip earthquakes within the transitional crust. So because of the obliqueness of the plate motion to the strike slip fault orientation, you will have these reactivated paleo rift faults in a sinistral sense of motion, and that is what we see in the Bengal Basin. The next question is, are there any other independent evidence to support our conjecture? And the answer is yes. What you see on the top and on the right are two figures which I have taken from both seismic and sedimentological work which has been done in the Bengal Basin. These are two cross sections which are shown on my map as blue lines, one which is a north-south cross section going across the Bengal Basin, the Dauki Fault and into the Shillong Plateau, and the east-west cross section which goes across the Bengal Basin and into the fold thrust belt. So what you see in both these cross sections are that underneath the Bengal Basin there is an attenuated crust, which is what we call as the transitional crust, which has these rift faults present within them. And what this paper also says is that the northernmost fault which bounds this transitional crust is the Dauki fault, and across the Dauki fault the crust is down faulted, and therefore this is another independent evidence to show that there are rift faults underneath the Bengal Basin, and what we say is under compression these are being reactivated as sinistral strike slip faults. So if you were to go to the field and observe the region across the Dauki fault, this is what you will see. So the map on the top left inset shows the region where I'm observing from, which is shown by the blue arrow. So if you are standing at the edge of the Shillong Plateau, you are actually looking at the Dauki fault, which is marked by the red arrows, which is down below the Shillong Plateau, which marks the boundary between the Shillong Plateau, and in the front you can see the flat Bangladesh plains. So the Dauki fault is the north bounding passive margin fault, which is now reactivated as a thrust fault which uplifts the plateau, and the ones which are in the front, which are slightly oblique to the Dauki fault, are being reactivated as strike slip faults underneath the Bangladesh plains within the transitional crust. If I compare the Bangladesh plains with a modern analog of a passive continental margin, this is what it will look like. So the Eocene hinge zone is the continental slope which separates the continental shelf to the northwest and the abyssal plain to the southeast. So in summary, what we are looking at is that the Dauki fault basically is the basin margin basement fault which continues as the Eocene hinge zone. The Dauki fault is responsible for the uplift of the Shillong Plateau, and the rift faults which are to the front of the Eocene hinge zone are getting reactivated in the present day as strike slip faults. Now if we were to go back and look at the rate of uplift across the Dauki fault and compare it with the present day measurements from GPS geodesy, then we should be able to kind of tell as to what the rate of uplift across the Dauki fault has been on the long term and how it compares with the GPS geodetic measurements, and that's something which we'll do next. Now I'm going to compare three different data sets to look at the uplift of the Shillong Plateau. The first one is from our study where we see a 12 to 13 kilometer offset of the Moho across the Dauki fault. The next is from Najman et al. 2016, where I'll use information about the uplift of the Shillong Plateau, which dates back to between 2 and 3.5 million years. So if I convert this offset of 12 to 13 kilometers over this period of time, that gives me a vertical uplift rate of 3.7 to 6.5 millimeters per year. Now if I make an assumption that the Dauki fault dips at 45 degrees, and this is something which I derive from Roger Billam and England's work on the 1897 Shillong earthquake, where they said that the Dauki fault is the south bounding fault of the Shillong Plateau and most probably dips at an angle of 45 degrees, then I can translate the vertical uplift to the horizontal convergence rate, which will also be quite similar, and that will be between 3.7 and 6.5. Now finally I use information from the GPS geodetic measurements which has been reported in Vernon et al. 2014, and what they say is across the Dauki fault from the east to the west, the horizontal convergence rate varies from 3 to 7 millimeters per year. So here you can clearly see that there is a clear match between the offset that we observe across the Shillong Plateau southern edge across the Dauki fault, convert that into a vertical uplift rate by using information from seismic data, and then if we compare or convert that into a horizontal convergence rate and compare it with the GPS geodetic measurements, they all fit together. Now the next question that comes to our mind is, if the Shillong Plateau is uplifted across the Dauki fault and it's actually overthrusting the Bengal Basin transitional crust, then what exactly is supporting this Shillong Plateau load? Because you remember from the gravity data we have seen that the Shillong Plateau doesn't have a crustal root. Therefore, there has to be a way to support this elevated Shillong Plateau. So we'll try and answer that question next. This is a map of the free air gravity anomaly across this region of northeast India. What you can see is that the Shillong Plateau has positive free air gravity anomaly. The region immediately south of the Shillong Plateau has a negative free air gravity anomaly. So you have this pair of positive and negative gravity anomaly, which essentially tells you that there is a flexed plate to the south of the Shillong Plateau. And what we can do is we can actually use the flexure of a beam and calculate what the response of that would be in terms of the gravity signal and match it with the gravity across this green box that you see on the map. So on the right top, what you see as the black line is the stacked gravity within this green box. What you see as the blue line is the fit to the stacked gravity data for an elastic beam with varying thickness, and the thickness is shown on the bottom left, bottom right figure. So it goes from 0 to 80 kilometers. You try and find the misfit between the observed and the calculated gravity for various elastic thickness, and we can clearly see that the minima is somewhere between 5 and 20 kilometers. So the elastic thickness of the plate, which is south of the Shillong Plateau, is about 5 to 20 kilometers, and that is what we think is supporting the load of the Shillong Plateau by flexure. Let us look at this closely by comparing it next with the seismogenic thickness. To compare the elastic thickness with the seismogenic thickness, what I'm going to do is I'm going to look at a cross section across this blue north-south line by stacking all the stations and the information about the crustal thickness and earthquakes which are in this region across this blue line in the yellow box. And I look at the depth distribution of the earthquake so as to see what the seismogenic thickness of the layer south of the Shillong Plateau is. On top you see the schematic cross section along that north-south line, and you can clearly see that the transitional crust has earthquakes which goes from a depth of 20 kilometers to a depth of 40 kilometers. So the seismogenic thickness of this layer actually lies within the transitional crust and is about 20 kilometers, which is comparable to the elastic thickness of the maximum TE, which is about 20 kilometers. So we can clearly see that the layer which is elastically strong is also the layer which actually causes all the earthquakes, and is the layer which is flexed and supports the Shillong Plateau load, which is overthrusting over the transitional crust. Finally, I'll look at the earthquakes in the Indo-Burman convergence zone. There are two very distinct category of earthquakes that you can see here. The first one is that there are shallow thrust earthquakes which deepen as you go eastward in the Tripura fold thrust belt, and it defines the Benioff zone of the under thrusting Indian plate or the subducting Indian plate beneath the Burman microplate. And the second are the deep focus thrust earthquakes which have an arc parallel slip vector, and this we think is indicating the flexure in the subducted slab. So we will look at these earthquakes by taking several cross sections from north to south and then plotting the deepest earthquakes or the depth to the deepest earthquakes to see how the seismogenic layer is flexed underneath the Indo-Burman convergence zone. So here we have taken 5 cross sections going from north to south, which are AA dashed through to EE dashed. What you can clearly see is that there is a dipping slab underneath the Indo-Burman convergence zone, which deepens as you go from the front or from the Bengal Basin into the east underneath the Indo-Burman convergence zone. These earthquakes obviously define more or less the geometry of the plate, and what you can clearly see is that as you go further to the south in this EE dashed cross section, these earthquakes become sparse, and but still they kind of define the downgoing Indian plate. What we then do is we look at the base of the seismogenic layer by looking at the deepest earthquakes, and that's plotted on the right bottom plot, where you can see that the plate dips as you go eastward, but it's also flexed in the middle, and that is because of the geometry of the subducting plate, which obviously goes down underneath the Indo-Burman convergence zone in a manner in which the center of it is flexed downwards. Now finally what we are going to do is we are going to take a 3D view across this region where I have marked the red arrow, and we will summarize all our findings. This is the summary of both the structure and the earthquakes across this region of the Eastern Himalayan and the Indo-Burman plate boundary system. The first thing that we see is that the crustal thickness varies laterally across this entire region. The Shillong Plateau and the Mikir Hills are underlain by the thinnest crust in this region, and the moe is flexed northward of the Shillong Plateau and the Mikir Hills. The second thing that we observe is that the Shillong Plateau and the Mikir Hills are underlain by felsic continental crust, whereas the region underneath the Bengal Basin is underlain by mafic transitional crust, which is of thickness about 20 kilometers, and this is overlain by the thickest pile of sediments varying between 18 to 22 kilometers. The Eocene hinge zone marks the paleocontinental margin or the transition from this continental crust into the transitional crust. The crustal scale Dauki fault, which bounds the Shillong Plateau to the south, is a basin margin fault which offsets the moho south of the Shillong Plateau by about 12 to 13 kilometers. By combining this information along with the uplift rate and with the GPS geodetic measurements, we can clearly see that the average vertical uplift from the long-term rates compares very well with the horizontal convergence from the GPS geodetic measurements. The entire crust beneath northeast India is seen to be seismogenic, and you can see on the bottom panel the plot of the earthquake depths for the 4 different regions, and you can clearly see that the earthquakes grow from the surface to a depth of about 30 to 40 kilometers depending on how thick the crust is. So the whole of the crust is seismogenic across this entire region. The deepest earthquakes are seen in the Indo-Burman convergence zone where you have a subducting slab. And finally, the Shillong Plateau load, which is being thrust southward, is supported by flexure of the Bengal Basin crust, and you can see that the elastic thickness of this crust lies within that transitional layer, and it's also equal to the seismogenic thickness that we derive from the earthquake depth distribution. If you are interested to know further about this study, I would refer to the 2 papers in which this has been published. The first one is in Tectonics, which is on the seismotectonics of the Eastern Himalayan and Indo-Burman plate boundary system. I acknowledge my co-authors, of whom the first author is my undergraduate student Ajay Kumar, and the other one, which is about the crustal structure, published in JGR Solid Earth, where I also acknowledge my co-authors Keith Priestley, Kajal Jyoti Bora, and VK Gaur. Before I end this presentation, I would like to acknowledge the contributions from my postdocs, PhD and BSMS students, and from my collaborators. Also, to do this kind of a work, you require data and funding, which I've received from a large number of organizations, and I've used a number of open source software for the data analysis and for making the plots, which I also acknowledge here. Finally, I would like to thank you for listening to this presentation.